Hi, everyone. Thank you for joining. My name is Haley Balkanoff. I'm a sustainability planner at the Capital District Regional Planning Commission, or CDRPC. You're here today for the Saratoga County hosted training, Understanding Solar PV Permitting and Inspecting in New York State by Chris Doty of BREC-Frontier Energy. For those of you that don't know us, CDRPC is a regional planning resource center that serves Albany, Rensselaer, Saratoga, and Schenectady counties. We foster intergovernmental cooperation, communication, collaborating, facilitating regional initiatives. We work with partners to help them address regional problems. Today's training is offered as part of NYSERDA's Clean Energy Communities Program, which provides match-free grant funding to local communities for clean energy projects such as facility energy audits and subsequent upgrades, HVAC upgrades, electric vehicle charging stations, LED streetlight conversions, among others. If you're interested in seeking funding for any clean energy projects for your municipal facilities, I'd be happy to provide free support and technical assistance. A few housekeeping notes before we get started. Our attendees join with video and audio off. Please use the Q&A feature to ask questions. This training will be recorded and slides available after the training is complete. Saratoga County staff will be issuing certificates of completion. For those attending for DOS credit, we received your training ID number as part of the registration process, and the county will aid in filling out training forms. If you did not provide a training ID, please reach out to county staff to provide that information. Before we launch into the training, I'm going to pass it off to Chairman Barrett to provide an introduction.
Thank you, Haley. Appreciate it. I just want to thank CDRPC for their help with setting this up today. I want to thank everybody that's joining. I was chairman of CDRPC years ago, so I understand the value that they bring to the Capital Region. And as Haley and I were talking about different training sessions that might be available for Clifton Park, I thought that some of these trainings we were discussing would be very good for everybody in the county to take advantage of, as there are billions and billions of dollars, both on the federal and state level, of public dollars that are being used to subsidize green energy projects. So the pressure for these projects to sprout up all over New York State and is extremely heavy, and it certainly is around our area. We are a very desirable place for many reasons here in Saratoga County, but certainly when it comes to solar projects, we've seen in Clifton Park and other areas that solar companies are looking very closely in our area for new opportunities. And as more subsidized money becomes available, there's new companies that are sprouting up as well. So this pressure will continue. And like a lot of things, we're all different in Saratoga County. Clifton Park, we've had several projects that are built. Some of you may not have even had one submitted yet, but likely you will. So how do you prepare for that? Understanding the technical realities around solar farms and also the planning and zoning aspect of solar farm applications. So there's going to be 2 training sessions. This is the first of 2, and we'll do more as they become available because there's other aspects to this, like negotiating pilot agreements and other things. But this is a great first start, and I really hope you find this training to be valuable. I'm sure you will, in understanding what to look for as we continue to have these applications come forward. So again, thank you, Haley, and all of our partners, and thank you, everybody, for participating.
Thank you, Chairman Barrett. Okay, Chris, take it away.
All right, thank you. I'm assuming everyone can see my screen. All right, thank you, and welcome to this course. We're going to go over, obviously, solar PV permitting and inspecting. We'll go. It's pretty detailed. There's a lot in this presentation, so we'll probably hold questions to the end. But as Haley said, if you can put your question in the Q&A, if there's time left over, we'll get to it. If not, feel free to email me, obviously at this email right here. And I'll be happy to get you, an answer. And so the purpose of this presentation is sort of to give you a 10,000-foot view of the Unified Solar Permit, which was put together by NYSERDA to help sort of streamline solar permitting throughout the state. And it's not really to give you answers to specific questions, because that would, we could fill a full 8-hour seminar with every specific situation. But if you ever need specific detailed help with a certain situation, feel free to email me or NYSERDA. I believe it's cleanenergyhelp@nyserda.ny.gov. And then they have a whole team of people to help. But I believe Haley said that she has your New York State training IDs. If you don't have them in, please put them in the chat or get them to her so that you'll get credit for this course. And we'll jump in here. Okay. All right. So this is this is the hour or the topic hours that you'll get credit for by taking this course. It's just sort of bookkeeping for your knowledge. Of course, if you want to get credit for this course, you have to attend it and watch the whole webinar. So here's some information on what you have to do. You have to log in around the start of the webinar and not leave until after the webinar, as you might expect. And if you somehow get kicked out, try to get back in as quickly as you can, because NYSERDA will look at the times that people are logged in. All right, so this is more just kind of bookkeeping. It's just you got to make sure that this is the primary thing that you're looking at on your computer. It's supposed to be your main screen. This is exactly what you would expect to get credit for this. All right, so here's what we're going to go through today. We're going to go through, as I mentioned, the solar permit, the Unified Solar Permit, or USP, that was created by NYSERDA. It's sort of a model permit that helps permitting authorities across the state. And then we'll walk through, what to look for in field inspections, the labeling that's required, and then we'll look at some common errors. And if we have time left over, we'll go through Q&A. As this is in webinar format, there are a number of questions throughout. So if you can answer those and just put them in the chat, or we'll keep an eye out and then go over the answers. All right, so the New York State Unified Solar Permit. This permit that NYSERDA put together has been adopted by over 300 communities throughout the state. It's an easy process, and it can be done by local law or just adoption by the local government. And it's really, they put it together as a best practice, and it includes requirements that can be applied to all solar PV systems of any size. It was made originally for residential, but it can be applied to any system. It's the difference between a small system and a large, megawatt system, is really number of panels, and there's some additional equipment needed, but it's all outlined in the permit package. So why is this such a powerful tool? The Unified Solar Permit was put together to streamline the process, but not skip steps or reduce the amount that the systems are looked at. So it provides a standardized process that's comprehensive, and it allows people to look at each system going from one side of the system to the other. We'll go through that in a little bit, in a consistent, predictable, and repeatable way. And the more times you do it, the better you get, and the more complete you'll be, and the faster you'll be. So this allows municipalities to save time and money and increase value. And it can be used by permitting authorities. It's good to provide to contractors so they know what you're looking for within an inspection and what they need for the permitting application. And it can be used just for community outreach, and so they know what needs to be provided. And the most important thing that NYSERDA wants to emphasize is they want to make sure that all installations are safe and code compliant, obviously. All right, so now we'll have a detailed look through the application itself. Here's the first 2 pages. It's really kind of like a general application. It provides general information, sort of kind of a cover sheet for the whole permitting application. There's not a ton of technical information, but it's more of like a who, what, when, where, and why of the system. And so here's the first section. The first section right here. You basically are just determining if you're eligible to use this permit application. It's things like the size of the system, if it's bigger than 25 kilowatts or not. Really, you can use the structure of the USP for a larger system, but some of the things required by the application only applicable to smaller systems. So you want to make sure it's less than 25 kilowatts DC. You want to make sure you don't need a special zoning permit or special use permit or things like that. You want to make sure that the solar installation contractor has all the licenses required within your jurisdiction. Make sure it's parallel to the roof, things like that. And so there's also sections, as you can see down here, where your jurisdiction can specify specific information that's not, going to be statewide. So if you have certain fees that you have to, collect to process the application, you can enter that here. You can have different payment methods and a number of different things. So it's a standardized process, but you are able to put in specific things to, for your jurisdiction that you may need. Here's, I believe it's the bottom section from this page, but this describes, submittal requirements for the application. This is, again, where you can customize specific fields such as fee schedule, payment methods. You could put in your website and email addresses so contractors know where to find you, or members of the public obviously know where to find you. And so this puts it all in one easy to find place. So if people have questions, they know who to contact. The third section down on the first page is where the application spells out approximate timelines that contractors can expect for either review and response or review and denial of an application. There may be, very different timelines. If you get an application on the first page, you see something that's very obviously wrong, you can just deny that right away. To go through the whole application takes a little bit of time, so that may be a longer timeline. And this is important because it gives solar contractors clear expectation on when they'll hear back from the permitting authority. Here we have the first section of page 2. And it really just includes, standard owner and dwelling information that's seen on all types of permit applications, right? It includes information that you would find on local tax maps, such as section, block, and lot number. And, that's for easy reference to municipal tax records for the AHJ. And this section is sort of probably the most technical of the first 2 pages. And you can see it's extremely technical. Not really, but it basically tells what's the system size in kilowatts DC, what type of inverter, and the location of the interconnection. And these are all important because if you know these 3 things, you can really get an idea of what you're going to see at the site, right? There's not a ton of difference between solar systems, there's specific differences between the designs, but generally the design will be similar if you have these, 6 different combinations. And so, if like I said, if you know which of these you're looking at, you'll be able to know what equipment you're looking at and a bunch of other things that we'll get into moving through this presentation. All right, so then this is the last page, I believe, on the first, the kind of cover sheet of the application. This includes contact information for the contractor and the electrician. Should have licensing numbers whenever they're needed. And the important thing here is you want to ensure that there are 2 signatures here, the property owner and the solar installation company representative. So that's both of them attesting to the accuracy of the information in the application. And that sort of puts the responsibility on them to have everything correct. And so here you can see there's 3 additional pages with a whole bunch of required information that have to be submitted with the application. This is to be compliant with New York State laws. It's construction documents and other information that's critical in evaluating the system. And so these requirements are basically the same for a 25 kilowatt system up to megawatt systems. It's like I said, the design of a solar system is not drastically different between a smaller system and a larger system. It's more just you're going to have bigger inverters. You're going to have obviously more solar panels. You have bigger size equipment. And as you're going through all these, some of them are not going to be applicable, based on if it's residential or if it's a larger system. But that's okay. It's a good, it's a framework to work from. All right. So, as I mentioned, there are customizable fields within the USP, allowing you to add specific local requirements when it's applicable. For instance, if you need a separate electrical permit, if a separate building permit, if you need fire department approval, things like that. And this is your opportunity to customize the standardized process for your area's requirements. And this allows you the necessary bandwidth to ensure that the proper information is requested that you need for your department to evaluate the system. And this also, makes it easy to review and also helps contractors not miss anything that's necessary in a given area. Obviously, you want contractors to have all the information they need to submit everything to you in a timely manner so that you can evaluate the system and the permit application. You don't want to have to hound them for everything every step of the way. All right, so as I mentioned, there's some construction documents that have to be submitted with this application. We'll go through these in greater detail as we move on. But the most important thing is the documents have to be stamped and signed by either a New York State registered architect or a New York State licensed professional engineer. And that's this professional taking responsibility for the quality and the accuracy of the design, along with the specifying of the equipment and the materials to be used. And it's the code official's job to determine the code compliance and make sure that it's safely installed and everything. But I doubt anyone on this call wants to be responsible for designing these systems and be responsible in case there's a failure. But that's the engineer or the architect's job, and they should be held responsible for that, and that's them taking credit for that. All right, so now we're going to look through some of the documents that we're going to be looking for. Different documents have different things that we need to check. So here we have, towards the top right here, we have the electrical details. You want to go through each of these items in a systematic way. Once you've done a couple of these, you can go through it much more rapidly. But there might be a bit of a learning curve at the beginning if you don't do a lot of electrical work. But it's all spelled out pretty completely in the USP document and the package. And this allows you, and it allows the contractor to consider each element of the design and provide the details necessary for you to evaluate the system. Basically what you want to do is you want to go from the modules to the array, or at the array to the utility interconnection, and make sure that each item is accounted for. You'll also need to have a roof or a site plan submitted, and this is basically like a document that details the specific location of all the major components, like if there's rooftop access, if there's setback requirements, it details where the panels will be, usually distance to the property line, things like that. And that's, for you to review and make sure that nothing is, if your jurisdiction has specific requirements that, solar panels can't be installed within 10 feet of the property line, and you can make sure that that is the case, and that prevents them from having to come back and fix it. And lastly, we're going to have structural information that they're going to provide. The main thing with this is it's very site specific. Every house is different. Every solar PV system is different. So it's site specific, and it basically is providing proof that the roof can handle the additional weight of the solar panels, and it's not going to cause any kind of structural issues. And so there's loading calculations with framing details, things like that. And like I said, each one of these is unique, so you can't use just rules of thumb. And there are checklists for each of these that we'll cover in a little bit. All right. So which inspections are required by the AHJ? Everything you want the contractor to know everything that you're going to be inspecting when you're on site. All this documentation clarifies all the items that are required for the inspection, so there's no surprises. Inspectors are not only going to be looking to see that everything is code compliant, but that the construction matches the proposed design. We'll go over that in a little bit. And as I said, you want to do this in a systematic way to reduce human error. If you do it the same way every time, it's a lot easier to just move through and do a complete evaluation and not miss things. One thing to keep in mind, NYSERDA does require that photos be taken on all the systems that they incentivize. And that's important because sometimes access is not easy. Sometimes things that need to be inspected are covered up during installation. So, the photos that are taken by the contractor, they're supposed to be taken by the contractor, but they can provide those to you, and that can enable you to move through more quickly for the inspection and not have to open up electrical panels, for instance, and be exposed to that hazard. So here we have question 1, which is which of these items is not a requirement of a solar PV permit application? You can put your answer in the chat. And we'll probably not linger too much on this because, as I said, it's a pretty full presentation, but I'm assuming that you guys all have read this. Maybe if this actually works. There we go. So the thing that is not required is the proof of property taxes or payment of property taxes. This is not NYSERDA telling you that you don't have to pay your property taxes. It's just you don't have to have proof of it within the USP to enable you to install a solar system. You do still have to pay your taxes. All right. So now you've received a permit package. It could be the package that your department receives or the unified solar permit if your jurisdiction has adopted that. And now we'll go through the tools within the package that'll help you review the permit package. So NYSERDA's developed a bunch of tools to assist permitting authorities in their work. We have the design review checklist and the field inspection checklist, in addition to a quality assurance checklist. All these are available through the NYSERDA website. They're comprehensive tools, and they're constantly updated, and they're designed by professionals with experience performing thousands of inspections. And we'll look at each of these in detail. And a lot of this can be found in the New York State Solar Guidebook, which is on the next page, and that's available through NYSERDA. This is a great resource, especially if you're not really familiar with a lot of solar PV systems. Has a ton of information. It's constantly updated, and they're adding new chapters to reflect different changes in the industry. So it's a super good resource. Obviously, you can find it right here at the NYSERDA website, and I would urge you to use that if you have any questions. All right, so starting with the design review checklist, and it's 3 main components: the construction documents, and the site plan, the electrical diagram, and the structural analysis. All these need to be looked at thoroughly to determine the code compliance of the system. And they're all available, again, in the Solar Guidebook, and it has code references included, which is super handy. And it's also printable, so you can just print it out and take it on site and go through when you're on site. All right, so the site plan checklist. This is really kind of a walkthrough of the components of the detailed site plan. It should include basic equipment information, including the locations of key components and any trenching, things like that, setback requirements. And this is to help avoid having to remove and replace equipment if they're too close to the property line. Here we have an example of a site plan. As you can see, it's sort of a map showing where it should have the tax information, the tax map parcel and things like that. Should have the location of the solar panels, distance to the property line, things like that, where you can get on the roof. And all things like that. It should have the location of the inverters, the disconnects, the power meter, a rapid shutdown initiation device, things like that. And one thing that you want to keep in mind is you want to make sure that this is stamped with the architect or the engineer stamp and signed. And you want to make sure it has the correct address and things like that. I think that's everything for the site plan. Next, we have the electrical checklist. You want to make sure you take time to go through every single item in the electrical checklist one at a time. I'm sure you're all very aware that electricity can be very dangerous. That's why you have to ensure that all the items are accounted for within this checklist. You want to draw a correlation from the checklist to the accompanying electrical diagram to make sure that everything's accounted for, and point out where there's details missing. For further follow-up, or you can follow up when you're on site. You can request pictures from the contractor or, spec sheets, things like that. And like I said, you want to keep track of things that don't match, so you know to pay extra attention to them during the inspection, the on-site inspection. This is just kind of an example of how you might mark these up. You want to make sure that you're looking at make sure that there are disconnects in the proper places. You want to make note of the type of solar panel that's being installed. If you don't see something that's on the checklist that is that is on the checklist but isn't on the design diagram, again, you want to follow up and make sure that it's accounted for. And you want to do all this obviously before you're issuing the permit. Make sure that everything is designed to be code compliant. This is just kind of more examples of things you'd be looking for, and if you go through all this, you can correlate it to the information that's on the right. We're not going to go through every single thing because it would take forever. But as you can see, this allows you to go through and verify that the equipment and the calculations are done correctly, and there's no missing pieces of information that would be necessary to evaluate the system. And now we're going to jump into the structural analysis. You want to, of course, make sure this is kind of what I was talking about before. This is ensuring that the structure that these panels are being installed on can hold the weight and will not have any structural issues having a bunch of extra weight put on the roof. You want to make sure that all the values are accounted for and the calculations have been filled out and done properly. These are all site-specific calculations. Like I said before, it's not a one-size-fits-all thing at all. All buildings are different and every PV system is different. So it's very important to make sure that these are the actual values for this, for this place. If you get 10 applications from a single contractor and they all have the same values, that's a pretty good indication that they're not really doing these evaluations correctly. So continuing on with the structural analysis, again, we go through this several times, but you want to make sure that the plans have the signature and the stamp of the professional engineer or the registered architect. Again, that's them taking the responsibility square on their shoulders for the design, and it takes the responsibility off of your shoulders. If you approve this and it doesn't have the stamp, that's sort of you approving the design, and that can come back on you. You don't want. I don't think anyone here again wants to take that responsibility on, just in case something bad does happen. But you want to make sure that they're stamped and signed so that responsibility is where it's supposed to be. All right. So you've done the design review and the permit's issued, and now the next step is the inspection. What do we do now, right? And also, have we considered the safety of the inspector, which is all of you? So inspections are required to follow NFPA 70E, which is the standard for electrical safety in the workplace. And of course, OSHA requirements are you have to abide by those, as in all parts of your work. NFPA 70E has traditionally been for electrical workers, but now that's been updated to include inspections as well. So inspectors do have to comply with the standard. And so this requires an initial risk assessment. And that's, thinking about things like if the electrical inspection will involve removing covers of, energized equipment, and and that will sort of determine if you need to bring personal protective equipment, PPE with you, or, things like that. And something else to keep in mind is, while solar PV systems are primarily, electrical systems, there may be other job site hazards present that may require additional PPE. For instance, I'm sure everyone here has seen PV panels that are installed on a roof, right? If you're up on a roof, especially if it's like a two-story building or higher, you may need fall protection. Or if the PV panels are installed on a steep roof, you may need additional protection to ensure your safety and ensure that you don't have any accidents. This is all having to do with the risk assessment procedure. This the NFPA 70E outlines procedures to reduce the risk for inspectors and electrical workers. And so what this sort of encompasses is it gives you a risk assessment procedure. You would want to go through the hierarchy of risk control methods, which we'll go over on the next slide. It gives you information on how to establish an electrically safe work condition. Typically, that's shutting down the system, right? If you have to get into it, you don't want it to be energized. That just opens you up to the potential to get electrocuted, which obviously everyone wants to avoid. It also has information on how to estimate the likelihood of an arc flash incident occurring. Arc flash is super, super important to be aware of because, it can cause a ton of damage to the inspector and property, and, it can potentially kill you. So you want to make sure you're aware of the likelihood of the occurrence of that happening. And it also gives information on how to select arc-related clothing and, using the incident energy analysis method. We don't have the time to go through all of this, so I will, let you guys look that up if you need to. Typically for a solar system, if you just shut the system down, particularly residential, you're not going to have, potential for arc related or arc flash incidents. So it's not typically something you're going to be dealing with in a residential situation, but it's definitely good to be cognizant of that potential risk. And so you used to really be able to just have like an electrician on site with you, and you can go through and they'll check things and tell you if it's okay. That's not really how it works anymore, though. Those days are sort of gone, and that's, it's probably for the best. You're the one doing the inspecting, so you need to follow the procedures to be safe. All right, so here we have the hierarchy of controls. This is a kind of a method of evaluation and selecting the most appropriate method of protection for personnel. The best control is always elimination of the hazard, as you can see here. That's basically shutting off the power to the solar PV system. If you have to check the connections for the inverter on the solar system, make sure they're tight. You want to shut the system down so that there's no power in those wires. And if you're, testing to make sure that the connections are tight, you don't potentially pull it out and electrocute yourself. The next best is replacing the hazard. Then, just keeping people away from the hazard. Obviously, you can't really do that when you're inspecting a system. Then, just providing warnings. That's not overly effective. People ignore those all the time. And then, you can change how people work around the hazards. And then the worst one is using PPE, right? That's essentially just accepting that the hazard's there and being like, well, we'll just deal with it and we'll try to protect ourselves. you want to eliminate the hazard if at all possible. So, that's that. Here we have question number 2. Which of these is not a hierarchy of control for electrical safety? And again, you can just, put your answer in the chat. All right, looks like there's answers coming in, which is good. They all, I think, seem to be correct. So we'll keep moving. The answer is C, right? You can't just reschedule work until after normal working hours. That's not mitigating the hazard really at all. It doesn't really matter how much power is being used. It matters that there's power there, and even if there's not a lot of power use in the building, you can still get electrocuted and you can still do a lot of damage from that. So it's not a method of mitigating the hazard. All right, so now we will jump into the field inspection checklist. This is a very extensive guide on what to look for throughout the entire system. It's based on the National Electrical Code requirements, and over 4,000 inspections done by NYSERDA. And those 4,000 inspections, this was created in, I think, 2020, so I'm sure it's thousands more by now. But it's very it's a great resource. It's printable, so you can take it right in the field. Then you won't miss anything when you're on site and have to go back. It supports a robust, thorough, and fair inspection process, because every site should be looked at the same. It does provide code references throughout, and that there's also you can find a bunch of these resources right here at this link. And these the slides can be I've provided them to the people organizing the training, and they can get the slides out to you, and that should have all these links and things like that. So hopefully you can take advantage of that. It's a super good resource. All right, so the field inspection checklist provides kind of an organized method of review, starting at one end of the system and going to the other. Typically, you would go from the array to the interconnection, or you could go backwards. It depends on your preference. But if you do it the same every time, that'll help you move through quickly each time and not make errors. If you're repeating the process, you just get better and better at it. So let's take a look at the checklist elements a little closer. We'll run through the different sections of the system. All right, so we will start at the array, obviously. This is essentially where the panels are located. Here you have a few examples of different types of arrays. You have ground mounted right here, you have pole mounted right here, and then roof mounted over here, obviously. As you can see, the modules on the rooftop may present some challenges to inspectors, right? This looks like a pretty steep roof. There's a bunch of different sections of the array. There may be access issues, right? It doesn't look super easy to get up here. And this is a great example of where construction photos provided by the contractor are valuable. Because if you have photo proof that they're all the same kind of panel, and you can just check one of them, then you don't have to get up on all these different sections of roof, and that reduces the hazard to you. And you can see, obviously, ground mounted and pole mounted arrays may be easier to access, the different connections, and get the nameplate information, things like that. All right, so at the array, the main thing you're really going to want to look at is the nameplate information for the panels, you want to make sure that it's the same as what was on the design package, the design documents. Here you can see a situation where they were planning to put in this SPR E20-435 panel, but they put in the SPR E19-320 panel. This is important because all of the different components within the system are designed based on the precise electrical characteristics of the modules. So, if you have different modules, you may have different power output, you may have different amperages in the wires, which can impact all the different components from the panels all the way to the interconnection. So you want to make sure that the design and what's actually installed are identical. And so kind of a good example of this is maximum system voltage. Or the open circuit voltage. So they can be higher for higher wattage panels, or even the same wattage modules from different manufacturers can have different, open circuit voltage. And all of your circuit sizing, overcurrent protection, wiring size are designed based on the energy production from the panels, obviously. So you don't want to just assume that the wiring and the other system components are still compatible. Another thing that you want to look for when you're looking at the array is the grounding of the array. I doubt I need to tell anyone on this call that grounding and bonding of the array is not just a code issue, but also a safety issue. The integrity of the grounding system is vital to any electrical installation, not just PV. And in a PV system, it's dependent not only on the conductors, but also on the equipment itself, which is used to carry the fault current to an overcurrent protection device or a fault detection system. So in the event that there's a breakdown anywhere along the ground fault path, the fault won't be detected, which can leave conductive parts of the system energized, and that can present significant shock hazard. Many times these are installed on roofs. So if you think about, for instance, a mason climbing on a roof to fix your chimney, and if they just accidentally touch one of the panels, they could receive a shock of up to 600 volts DC or more. And that can be prevented by careful grounding and bonding. And so there are, traditional ways of bonding, which you would see like with a ground lug and a copper wire. That's what you would more likely see and older installations. A lot of times now they're going more towards integrated bonding, which is, you can see an example of here. And that's bonding that it serves a dual function. It keeps the whole system together and mounted, and it also provides a ground path throughout the system, to allow the overcurrent protection device to function. And a lot more systems are moving towards that. And on the left, you can see this is just a kind of a poor installation. You can see the screws coming out. It wasn't tightened very well. That can, eventually come disconnected, and it could potentially, change the ground path throughout the system. And so it's critical that the equipment that's used to bond and ground the system is suitable for the environment and the application. Obviously, solar panels pretty much always have to be inside or outside, obviously not inside. There's a lot less sun inside, as you might all be aware. But they have to be able to withstand, outdoor conditions day in and day out throughout the whole year. So you want to make sure that all of the components that are used to install the system and bond it and ground it are rated for outdoor use. So here we're continuing on with the array. Again, it's critical to use outdoor rated equipment. Here we have a situation where wires were bound up using a UV rated zip tie. The white ones are typically not UV rated, and they can degrade in the sun over time. They can, eventually they'll get brittle and break, and then you just have a bunch of wires hanging down on the shingles. Shingles are pretty abrasive, so, as they're moving around in the wind and things, they'll wear away, and then you'll have exposed copper conductors, which of course we all want to avoid, right? All of these systems, or typically PV systems, are rated and warranted for 25 years. So you want all the system components to also last that long. And so I talked about the one on the left. On the right, you can see this lug is starting, the screw is starting to rust. That means it's not, rated for outdoor use. Eventually, it's just going to rust through, and it'll likely break apart and come on or disconnected. And then you have a interrupted ground fault path, and potentially a very hazardous situation. So that's one thing to keep in mind. When you're looking through these systems, if you see, screws or ground lugs with a lot of rust, that's an indication that they didn't use the proper equipment. All right, so now we're going to jump into DC optimizers and microinverters. A DC optimizer is essentially a DC to DC converter that takes whatever amperage and voltage is produced at the solar panels and converts it to the voltage and amperage required by the string inverter. If you have a DC optimizer, you're going to have a string inverter with the system. A string inverter basically takes the DC voltage from the panels, from all the panels, and converts it to AC power all at one location. A microinverter is basically a tiny inverter, as the name implies. And typically when you have those, there's one for each panel. It converts it to AC electricity right at the panel, and then you have all AC wire runs coming back to a combiner panel. And there's advantages and disadvantages to both of these. We're not really going to go over all the advantages and disadvantages, but that's sort of an overview of these two pieces of equipment. There are specific labeling requirements for each, which we'll go over a little bit later. And so basically what you want to do within this section is you want to verify that the equipment that's on the design documents is what's actually installed, and you want to verify the proper grounding and bonding throughout the electrical path. And so one thing to keep in mind is microinverter systems, they do meet rapid shutdown requirements. By design, they all have this kind of as a feature, but they do also require proper labeling, which we'll again go over in a little while. A very important element of installing and inspecting this type of equipment is kind of a thorough understanding of the installation manual. And that may include specific considerations for that device, right? It could be how you mount it to, wherever it's mounted, or specific bonding and grounding requirements, or, limitations on string configurations, things like that. So you may have to look through the installation manual for these things to get those specific requirements. But if you want to have a safe code compliant system, it's worth it to obtain those and look through them. So one way that DC optimizers and microinverters are similar is the rapid shutdown features. They both have them, and so this is a method in the code where DC conductors are shut down on a level close to the array. If power's interrupted, the system shuts down to prevent live DC conductors in the system or the building. Using this feature that they have already installed is a way, an allowable way within the code to provide, rapid shutdown to the whole system. That's an important point. You don't have to have a separate rapid shutdown method if they already have it. So here we go. Question 3, true or false? Using microinverters or string inverters with DC power optimizers is one way to meet the rapid requirement, or the requirement for rapid shutdown within a system. Let me throw your answer in the chat. All right, we have
a question as well. Albert
Okay.
Gilman. You can unmute, I believe, to speak. Or you can always pose your question in the Q&A as well.
Yeah. Yeah, if you want to do that, I'll probably get to that toward the end, or if I see it come in. Okay. All right. Yeah. But so we'll keep moving through. This is true. You are able to use these two pieces of equipment to meet the rapid requirement shutdowns, or rapid shutdown requirements, sorry. Within the code. All right, so now we're going to go into the rooftop. The guidebook has a section for rooftop PV attachments and penetrations. So in addition to verifying that they're present, you have to verify that they're installed properly. The guidebook gives examples of proper installation. You may see, flashing that's not installed correctly according to the manufacturer's instructions, or things like that. It's important for contractors to follow these guidelines and for inspectors to know what to look for. So on the left here, you can see this is sort of a weird angle to look at this, but this over here is the top of the roof, and over on the right is the bottom, so it's actually going down to the right. And you can see the flashing is installed up underneath the shingle. That's the correct way to install these, so water will just shed down over it. So that's done correctly. Over here, this is the correct piece of equipment that you would use for a roof penetration, the rubber boot. But this would fail in the inspection because it's not installed properly. It's supposed to, all that the rubber piece should go up so the water just sheds right off of it. But here you can see it's pushed down, and then water will pool in here. And I don't know if all of you know, but in New York we have pretty cold winters, except this past winter. But you'll likely get ice and freezing and thawing and things like that, and that'll cause stress on the rubber, and it can cause failure and cause the seal to fail, which obviously you want to avoid. There we go. Here we have question 4. So true or false, properly installing roof flashings and sealing roof penetrations is a critical part of installing rooftop PV systems. feel like this one is kind of an obvious one, and all the answers coming in are great. That is true. Obviously, you don't want to have, you know, poorly installed roof penetrations that will leak and cause damage to the building, or cause mold, or require the homeowner to have costly repairs. All right, so now we'll look at junction boxes. So if an enclosure is mounted on the roof deck, it has to be properly flashed and sealed, as you can see on the left. This is properly flashed and sealed. However, a conductive enclosure, this is a metal enclosure, so it's conductive. If you have electrical wires coming through here, it's considered likely to become energized, and it's also supposed to be bonded and grounded throughout the ground path. You can see a ground lug here, and they have the ground wire running through, and it's never terminated in this enclosure, so that would fail. In the picture on the left, or that's what I was just talking about, the one on the left. On the right, this box is non-metallic, so it does not have to be grounded, because a non-metallic box is not conductive. And one thing to keep in mind is, if you don't have like bare wire ground running through the conduit, and you have metal conduit, you have to specifically bond the conduit, so there's definitely a ground path moving through the whole system. And it's important to keep in mind, in both of these situations, the enclosures have to be rated for the environment in which they're installed, which is outside. So now we'll talk about string inverters. This section of the checklist asks for basically equipment verification. It's vital to ensure that the actual installation matches the design submitted. And conductor sizing is based on the information provided by the manufacturer. And if a contractor substitutes the inverter model, it can be oversized for the conductors carrying the output current, which can cause wire insulation failure, or in real bad cases, it could cause the wire to melt and could cause fires and things like that. So this is typically verified by looking at the inverter nameplate, which is usually on the side or underneath the inverter itself. And in this case, you have DC conductors coming down from the roof. And you can see this label here. Well, you probably can't see it, but we'll show a better example of it later. When you have DC conductors in a metal raceway, you have to label that raceway every 10 feet, showing that it does hold DC wiring. And that's for in case of an emergency, if there's emergency personnel and they need to know that there could be live DC wiring in that conduit, if they have to do anything with it. More on string inverters. Here we're taking a look at the conduit bonding that is crucial to a safe installation. You can see this is a non-metallic enclosure, and the conduit coming in and out over here and over here are metallic, so you have to make sure that the ground path from here to here is continuous. So you have to make sure, you can see there's a ground lug installed in here, and these little clamps allow that ground path to continue from this conduit to this conduit. And you also want to check for conductor sizing and markings, as well as fusing requirements. Fuses for solar PV systems they have to be rated for solar, and you can't just use any DC fuse. And so fuses have to be rated for 600 volts DC in residential applications and 1,000 volts DC in commercial. All right. So lastly, we're going to take a look at the labeling requirements per NEC 690. This inverter has a disconnect handle built right into the inverter right here. It has to be labeled as the DC PV disconnect, and also that it has a rapid shutdown feature. String inverters have red rapid shutdown labels. And labeling is super important for future maintenance of the system, and so that people are aware of specific hazards, within the enclosure, within the inverter, or whatever piece of equipment you're looking at, and also for first responders if they have to do anything with it. So here we have an AC combiner panel. This is where multiple arrays may be connected to be combined into one single feed before going to the interconnection. This is similar to a sub panel, but it's slightly different. So it does require overcurrent protection, which is these breakers right here. And they have to be appropriately sized. The enclosure needs to be properly bonded, and the neutral must be isolated from the enclosure. So that's a big one for the AC combiner panel. You have to ensure that the neutral is isolated from the enclosure. In this case, the contractor did an accurate job of that, and they did not bond the neutral conductor, to the equipment grounding system. So this one was well done. Now we're going to start talking about the interconnections. This is kind of a simple drawing of where a load side interconnection is made. This is where the inverter output is connected on the load side of the service disconnecting means, which is typically a backfeed breaker or a sub panel. And so these are typically located on the opposite side of the panel from where the utility power is coming in. This is so that you don't overload the bus bar within the panel. So for example, if you have 100 amp service, and you have something that's just sucking power on your panel, and you're using 100 amps of service plus whatever you're providing for your solar, at no point in this panel should there be over 100 amps. You want to prevent that. So that's why you have the power coming in from the utility on one side and the power coming in from the solar on a different side. And so the thing to keep in mind here is the sum of the backfeed breaker, which is the inverter from the inverter, and the main breaker panel, or main breaker, they can't exceed 120% of the bus bar rating. So for instance, if you have 100 amp service coming in and you have 100 amp bus bar rating, you can have a 20 amp backfeed breaker and it'll still be acceptable within the code. And so if you have a bus bar that is rated at higher than 100% of the utility meter or the main breaker rating, you should be able to locate this backfeed breaker anywhere within the panel. So when you're looking at the load side connection, you need to look for your circuit ampacity. That's the amount of amperage that the circuit can carry. And so to figure this out, you want to look at the inverter nameplate, which shows the max output current here. You want to ensure that you size the breaker and the wiring to hold 125% of the rated output ampacity of the inverter. And this is crucial to get right, because if you undersize the wire, you can cause dangerous situations where the wires will overheat, or you could cause fires or things like that. As with all conductors of the system, the overcurrent protection has to be properly sized. Again, you want to size that at 25% higher than the rated output of the inverter. So you want to ensure that the wiring or the overcurrent protection is rated for 125% of the maximum output current of the inverter. most backfeed breakers will be double breakers, which corresponds to what's in most homes. So you'll have equal distribution on each leg. Obviously, in like more commercial applications, you might see, differences. Here we can see the requirements for circuit identification. On the right, you see a good example, well, an okay example of a directory for a microinverter system that includes, or on the right, you see a good example of a directory for the microinverter system that shows which panels are going to which circuit. And that's a valid way to provide this information. On the left, you can see semi-legible circuit directory within the electrical panel. You want to make sure that everything is legible and properly labeled. But this is a lot better than you see in a lot of places. A lot of places don't even label the panels or the breakers. So that's something you want to keep in mind. It's important for future maintenance and troubleshooting. All right, so here's a simple look at a common load side connection calculation that's used to determine if the panel board is large enough to accommodate the PV system. It's known as the 120% rule. So you have the main breaker, which is 100 amps, and then you have a 20, or at this site you would have a probably a 20 amp breaker for the backfeed breaker, but the inverter current, the max inverter current is 14.4 amps. So you'd multiply that by 125%, you get 18. So this system is fine to install with a load side connection because 118 is less than 120% of the main breaker and the bus bar rating. So that's how you do that. Now we'll talk about the supply side connection. So this is when the inverter output is connected on the utility side of the main service disconnect. So this is sometimes referred to as a line side connection or a line side tap. And since the supply side connection is very similar to a new service entrance, the NEC requires that the disconnect be rated for such. And you need to have 60 amp conductors, or rated conductors rated for 60 amps going from your inverter output to the where they connect into the supply side connection. And I believe the main service disconnect also has to be rated for 60 amps. And let's see. Yep, so I think that's everything for this slide. A supply side connection must have a service rated disconnect switch with a minimum rating of which of these? And falling a little bit behind on time, so I'm gonna zip right through this, but yes, the answers coming in mostly are looking good. It's going to be B, 60 amps. That's per the 2017 NEC code. All right, so moving on, with the supply side connection, you have to ensure that the conductors are sized appropriately. Again, you verify this by looking at the inverter nameplate for the max continuous inverter output current. Just like we did with the load side connection, multiply that by 125% for continuous load, and you verify that the conductor size stamped on the wire itself. You can look that up online to determine what wire can hold what amperage. So that's how you do that. Another thing in the 2017 NEC, which is the one that's adopted in New York State, it states that the length of the supply side conductors can be no longer than 10 feet in length unless other means are taken to protect them from protect them, such as current limiting devices. You can see here, A is where the inverter output is fused and changed to service conductors, which are the 60 amp rated conductors. And they go to the breaker panel and they connect in on the supply side of that main breaker. And so that length, that total length from A to B can't be more than 10 feet. And so in light of the fact that supply side conductors are similar to a second set of service entrance conductors and that they are kind of unprotected from utility side current potentials, the disconnect that serves a supply side connection must be bonded similarly to a service panel, where the neutral and the ground are bonded to the enclosure. So this is different from what we saw earlier with the disconnect we saw earlier. You can see here the neutral and the ground are bonded together with this green bonding screw, so that's done correctly. And so that also bonds the enclosure and grounds it so that, you know, it's safe to touch, basically. So here we have another supply side connection. The main difference here is that there's no bare ground conductor, so the ground is run with the green ground conductors. That's typically what you'll see. And you can see it crimped together on the left side right here to the conduit so that, you know, there's a good ground path throughout the whole system. This is a metallic enclosure, but the connections coming in for the conduit are typically done with knockouts, which are, you know, pre-punched basically through the material. And if you're just relying on the enclosure touching the conduit to provide a ground path, it could potentially not have enough area to move through for the current, and it can melt out these knockouts and cause a disruption in your ground path. So you need to bond them together, and that'll remove this problem. All right, so here you can see some of the labeling requirements for this type of connection. You have the, you know, traditional electrical shock hazard, you know, labeling, and the PV AC disconnect as well. This would probably be for a backfeed breaker inside the panel. So you want to ensure that people know that the PV AC disconnect is there. And of note is that the PV part of the code probably has the heaviest requirements for labeling that there is. So, you know, it's kind of difficult to get right, but it's all important to maintain safety of the system. So you definitely want to familiarize yourself with that part of the code. And so next we have another question. So which of these options is not an accurate description of a solar PV system? I don't know, people, yeah, it looks like some are coming in. Maybe. But we're gonna keep moving through because, as I said, I'm getting a little bit behind. The answer is B. A load side connection with a capacitor diverter is not a solar PV system. A capacitor diverter is not a real thing. So that does not qualify as a solar PV system. All right, so within the New York State solar guidebook, you'll find a detailed labeling guide. Labeling can be very challenging, even for experienced contractors. You know, things to remember are labels have to be durable. They're supposed to last 25 plus years. They should be placed in manufacturer recommended areas, not covering other labels, of course. Colors are predetermined by ANSI and OSHA, so they have to have the correct coloring. So typically for solar panels or, you know, solar PV systems, they'll be yellow, orange, or red. So if you see like a different color label, it's probably wrong. And so the main thing to keep in mind is the most dangerous label is a wrong label. It's not a missing label, right? If there's no label, that's bad, obviously. But if you have the wrong label, it can provide whoever's working on the system with kind of a sense of security that they know what they're getting into, and they may, act based on that. And if it's wrong, then they can potentially get shocked, or, worse, they could potentially die. So, um, the worst thing is a wrong label, and then after that, it's a missing label. So now we're going to go through some examples of labels that are required for solar projects. Again, all PV signage is yellow, orange, or red in color, so it's easily identifiable for electricians and code officials to find. So here you have the traditional arc flash hazard warning. This is required on electrical equipment, switchboards, panel boards, control panels, meter enclosures, and motor control centers that are in other than dwelling occupancies. Again, this is obviously a very important warning label. Arc flash incidents can cause death or serious injury, so you want to make sure everyone's aware of that. Here we have the service disconnects that are labeled, and they have to be labeled with permanent plaques. You can see here they are, and they also show, or they give information on where the other disconnect is. So with a solar PV system, typically you'll have two disconnects. Of course, the service disconnect for the utility, and then the solar disconnect, which is typically the backfeed breaker. So you want to make sure that if someone turns off one, they know that there's another one, so that when they're working in that panel, it is electrically safe. For supply side connection, NEC 230.2E requires a directory of the location for each service disconnecting means. So you can do that via a map, like on the right here, showing where the disconnects are, or you can do it via a plaque that tells where each disconnect is located. Again, so that whoever's working in it can shut both down and ensure that they're working in a safe condition. The NEC also requires these markings right here on PV system disconnects. You have the PV AC disconnect or PV DC disconnect. Obviously telling where the disconnects are. And they're red so that it's easy to see. And again, if you disconnect the system from the utility, the power's going to be off, but for a PV system, that's not necessarily the case. You always need the electrical shock hazard where there's potential for electrical shock. So that's an important one. And again, you have to make sure that the labels are suitable for the environment in which they're installed, so that they last the expected life of the system. Again, more about specific labels is the electrical shock hazard labeling. You want that on all your switches and circuit breaker panels, so that people understand that there's a hazard and to be careful. Moving on, here we have the PV AC disconnect label. So anytime you have an inverter output, that's what's known as an interactive system point of interconnection, and you have to provide this label with the rated AC output current and the nominal operating voltage. So something to keep in mind is NYSERDA does not allow writing in on these labels. They want it to be engraved or printed. One second. Excuse me. So if it's engraved or printed, it's going to last a lot longer. If you just, even if you use a Sharpie and you write in, whatever these values are, it's going to fade and it's going to disappear by the end of the system life. So, when someone comes in 20 years to service the system, there's going to be nothing there. They're not going to know what they're getting into. So you want to make sure that these are printed or engraved. Here's what I was talking about earlier with the DC power going through the conduit. You have to make sure that all DC conductors are in metallic raceways or metal clad cable inside a building. They also have to have this labeling, which is the PV power source warning label at a minimum of every 10 feet. And that's when it's DC conductors. Many people don't like the look of this, which is understandable, but so a lot of times they'll run the conduit through their attic space or use microinverters to avoid having to see that, because if you use microinverters, it changes to AC right at the panel, and then you don't need this label. Here we have the DC PV power source label, and that has to be on an inverter integrated DC disconnect or a DC combiner with a disconnect. This label gives important information to those who will maintain and repair the system in the future. So you have to label the max voltage, the max current, and the max current of charge controllers if installed with energy storage. NYSERDA is planning, I believe, or they have it out for public comment to have a program for energy storage incentives if people install them in their house. So you may see that more and more frequently. So that's something to keep in mind. Here we have an example of the required labeling at the interactive system point of interconnections. You need the AC output current and the AC operating voltage. Again, you want to make sure that they're printed or engraved, not just written in. And a lot of times these labels are missing or incomplete, or they're not suitable for the environment. They wear away, and then you have no label left, and 10 years down the line, and someone coming to service the system doesn't know what's there. So you want to make sure that it's rated for outdoor conditions, because a lot of these will be outdoor. Here we have so this is just more on the labeling requirements. These labels are for rapid shutdown. Red would be used for a string inverter system. Yellow is used for DC optimizers or microinverters. New York City, something to keep in mind. I don't imagine anyone in Saratoga County is inspecting systems in New York City, but you never know. So New York City has adopted an earlier version of the NEC, which they are able to, they specify their own thing because they're sort of their own beast, I guess. And that doesn't include a rapid shutdown requirement, but NYSERDA accepts the 2017 NEC, which does. So they are able to specify that a rapid shutdown be installed, even though that's not included in the current New York State minimum code. You could potentially see a situation where someone refuses to install that, and they just don't get the NYSERDA funding for the PV system, but that's kind of not likely. So here we have the point of interconnection identification. This is a requirement, and it's to simply identify all sources of power supplied to a bus bar or a conductor. You can see, it allows someone to know that there's two power sources, and the second power source obviously is a PV system. You would also want to have some kind of way to tell them where the other source can be shut down. And this is important because it may be the first indication that PV is installed in a building. You know, if the PV system is on the back of that building and the electrician comes in through the front, they may not even know that it's there. Here's another label required by the NEC and OSHA. It's, you know, pretty self-explanatory. Again, it's to alert someone to make sure that they need to make sure all disconnects are closed before, or open, I guess, really, before working in a panel so that they can avoid it being energized while they're working on it. Here's the power source output connection label. This shows where the PV power is coming into the panel. You want to make sure that it doesn't get moved. Obviously, it says do not relocate this overcurrent protection device, and you want to make sure that the label stays with the overcurrent protection device. This is again to avoid overloading the current to the bus bar. Here we have a situation where the installer didn't label the sub panel, so who knows which breaker goes to what. So, you know, that is potentially a problem down the road if someone has to shut the system down. But having this, you know, properly labeled is part of the general electrical code, not just the PV code. And so, you know, that still has to be followed. So which of these options does not describe a PV warning label? We've gone over this a few times, so probably just gonna go right through here because, again, I don't want to take up more of your time than you guys want me to take up. So here we have the one that is not a PV warning label is the green and white background. Solar labels are pretty much always red, orange, or yellow. So now we're going to go over just a few slides on photo inspections, and then we'll jump into common errors that we see. So can a comprehensive inspection be done by looking only at photographs? The answer to this is yes, but it very much depends on the quality and the quantity of the comprehensiveness of the photo collection. Photo inspections are done through the quality assurance program for NYSERDA to save dollars by not making someone go to an in-person 4-hour inspection. And something to keep in mind is sometimes well-built systems will fail a photo inspection because of the quality or the quantity of photos was not good enough to make a determination. So it's on the contractor to take the proper photos and the proper quantity of photos for someone to make it an evaluation. So NYSERDA has been doing these for a long time now. Permitting authorities can choose to require photos to supplement an in-person inspection to avoid making multiple trips to a site. And they can really kind of tell a story of how things were constructed and save the inspector time. It also can improve inspector safety by reducing exposure to hazards like ladders or energized electrical equipment. And for instance, you could have photos of trenches and walls before being closed, which will reduce the number of trips that the inspector needs to make to a site. So this allows the jurisdiction to save money and save time by not having someone have to go to a site 4 or 5 times just to, you know, see every step of the process. And so NYSERDA's had a lot of success with this. It can save a lot of money. And you know, this is basically just you're welcome to start implementing this in your jurisdiction if you so choose. What are some of the reasons to use photos to supplement inspections? Again, we're gonna just blast right through this because we're kind of short on time. The answer is D, all of the above. It can tell a story of how things are constructed and save you time. It can, you know, improve safety. And It can provide photos of, things that were sealed up before the full system inspection or installation is complete, so you can reduce the number of trips to the site. All right, so now we're going to look at some common installation errors. This hopefully is the most important, or not the most important, the most interesting part of the presentation. And so let's jump into it. So, we've talked about this kind of ad nauseum throughout this presentation, but it's important to ensure the system grounding is done properly. This can be done, through integrated bonding, like we have here. It can be just a ground lug moving with a copper conductor moving through the system. A lot of times now there are some PV panels that have plastic frames that don't need to be grounded, but you still have to make sure that there's a good bond path throughout the system. And so, let's see, if there is no path throughout the system, it can cause, an overcurrent protection device or the pathway for fault current to not trigger one of these, the fault detection equipment. And then it can cause someone to be electrocuted or, cause someone to die. Again, here we see the integrated mid clamp that provides the bonding of all the modules. And there are other ways to do it too. We'll see a few of them throughout the next few slides. So here's an example where a contractor attempted to accomplish the bonding requirements with a copper lay-in lug on aluminum frames. However, as you can see, they've corroded, and the copper lug has actually disconnected from the module. So this module is no longer connected to the ground path, or bonded. So you can also see that they did the same thing over here. Looks like it's not going to last that much longer. And then eventually this one will be also disconnected. You can see more corrosion right here. So you want to make sure that you are looking for things like this to make sure that they used appropriate materials for installing the system. And this happened just between the installation of the system and the QA inspection, so not that much time. And the screw had already corroded to a point where it broke away from the panel frame. And so this is partly because it's dissimilar metals and they're not compatible, and also because it's not rated for the outdoor environment, which helped it move along to failure. In many applications, you'll see that contractors have bonded the rails themselves as a way to get through the path, or provide a path through the system. And they do that through a lay-in lug like the one pictured here. However, this system, or this lug, was installed with the screw that's not rated for bonding purposes. So it's kind of like getting right into the nitty-gritty of the code. But typically for this, you'll need a finely threaded machine screw. You want to make sure that there's at least 2 threads on the metal of connection for this situation. That's to ensure that there's proper amount of area to hold the current that could potentially be moving through here. So this one would not pass the inspection. One of the most common installation errors that we see on a rooftop particularly is where the conductors are not properly supported, and they're just laying on the roof where they're subject to damage by wind, snow, ice. The wind can move those around, cause them to run along the abrasive shingles and wear away that way. So that's a potential problem. The wires can also catch debris moving down the roofs, and which can cause drainage issues and then cause problems with the roof. And another potential hazard for rooftop installations is squirrels and other animals like to nest underneath the panels, and then they chew on the wires, which can, cause problems. They have what's called a critter guard, which is basically like a metal or a plastic mesh that surrounds the array and blocks the animals from getting up underneath the array and making nests. So that's something you would want to keep an eye out for. As I think I mentioned earlier, PV systems have to be, they have to use PV rated fuses. So you want to make sure that the fuses, in this case, this was done correctly, but you want to make sure that the fuses are rated for PV and obviously DC rated. Here we have a situation where this is pretty common. The fittings used to provide strain relief for the wire coming into this junction box. It was not. It looks like it's damaged actually, but it isn't snug with the wire, so it's not going to really provide any good. It's not going to stop water from getting in. It's not going to provide any kind of strain relief. So that should be disconnected and reinstalled. And then on the left, the flashing is good. You can see it goes up underneath the shingles. It's rated for outdoor use. However, the contractor, instead of running the wires through a knockout, they just ran it up underneath the cover of the system or of the enclosure, which basically leaves it wide open for rain and anything else to get in. They would need to disconnect this and run it through the knockouts to ensure that it's installed properly. And also, this red one and possibly the blue wire nuts are not rated for outdoor use. And even though this is like an enclosed space, it's still installed outdoors. It's going to have the humidity and the temperature of the outdoors environment. So it has to be rated for, all the equipment has to be rated for outdoor use. Here we have a situation where we see what's called galvanic corrosion, and that happens with the direct contact of dissimilar metals. We saw that with the aluminum panels and the copper land lugs. So here's both of these situations are showing how much corrosion you can get. This one's not as good. You can barely see it up here, but you can see the copper and this fitting, or it's probably aluminum, are in contact and it's causing corrosion. And then here you can see a much worse version of that where there's corrosion occurring. This is in a pretty wet environment, so that helps it, corrode faster. And a way to avoid this would be to use insulated conductors, and there's other methods too. Here we see a similar thing. Raceways are not really approved to have electrical wire carried on the outside of the conduit. Pretty much the only thing you can have running on the outside of a conduit is like data wire. So you can see they ran the ground wire or the ground conductor or all along the outside of this conduit, and wherever it's touching, it's corroding. That's because again they're dissimilar metals and they corrode when they're in contact. So over time, that's going to just corrode all the way, and then you'll have a disconnected ground path. These conductors in this image are not protected from physical damage. You can see it goes up over this the racking system and over the sharp edge of the shingles. Eventually, these are gonna fail. These conductors will be in contact with the roof, and they'll wear away until the copper is exposed, and then they'll fail. likely well before the 25 years that this should be designed for. And this contractor should have used conduit to protect these conductors going around the edge of that. Here we can see a problem with enclosures themselves. Code allows for the use of what's called weep holes, which are holes drilled into an enclosure that allow water to exit the enclosure to help avoid pooling. Weep holes are used to prevent moisture from accumulating in the enclosure, as I sort of just said. Here you can see that the water line sort of ends right where the weep hole is. So this is showing that it, the rust line, that's where the water was. So it is showing that it's effectively draining the water. And obviously you want to keep in mind these should not be sealed, as the whole point is to keep them open to allow water to exit the enclosure. This is kind of an interesting situation. We have an outdoor rated enclosure that was just not installed properly. You can't really see it in this picture, but the conduit entry point isn't properly sealed at the top of the enclosure right here. And so water got in, and luckily the wire nuts were such that they were not down in the pool of water. But the only reason they could see this was because it was removed in the winter, and obviously this is ice down here. But what happened is water filled up this junction box to a point where it got high enough and it could go down one of these conduits on the side. It looks like the one on the right. And obviously water is not something you want in your electrical system. That can be quite hazardous. So that's kind of a pretty bad mess up. So they would want to reinstall this junction box properly so that water doesn't get in. Here we have an enclosure that's not only suffering from water buildup, as you can see in the bottom, but the lugs on the conduit are not rated for wet environment. You can see they're rusting, and eventually they're going to wear away and break off. The wire nut terminations also are not rated for the environment. This is a situation that would have been well served by the installation of a weep hole, like we just talked about in the previous slide, or the previous one before that. And on the right, we have a situation where we have conduit. This is a flat roof with solar panels installed on it. We have conduit coming out of this junction box, and it goes up so that the wires can go over the racking system. But when you have a situation like that, rain can just get right into this hole, and then it just drains right into the enclosure. So, that provides like a highway for water entry into the electrical enclosure, which again, you always want to avoid. Here we have conduit passing from the outside of a building to the inside of a building, and it was not sealed. There's potential for condensation buildup where the warm building air meets the cooler outside air, or vice versa. And once the condensation forms, there's no place for it to go but back into the conduit, and then into whatever panel board or whatever they have inside the wall there. And again, you want to avoid any moisture getting into these situations, because it can cause massive problems with your electrical. And this is not just a violation of the electrical code, it's also part of the energy code. So since there's an energy component to it, if they sealed that, then there would be basically no flow of air and no potential for condensation. We saw kind of an example of this earlier. We have metal conduit, and this is a non-metallic enclosure. Well, it is, I believe it's actually metallic on the inside, but plastic on the outside. So you have to make sure that the inside is bonded to the ground path via a grounding wedge. You'd have to make sure that this conduit here coming out of this panel or this structure box is also bonded. Here we have a situation where you have a disconnect where the wires were not installed correctly. You can see down here a non-contact voltage tester is being used, and the system is open, but there's still voltage in where the fuses are. What happened is they installed the conductors that should be going in to the bottom. They installed them at the top, and then vice versa. And so no matter what position this disconnect is in, the fuses are always energized, and so you can never really safely change the fuses. So that's an important thing to keep in mind when having disconnects installed. One thing to keep in mind is these for DC situations, non-contact voltage testers don't always read, so you have to be extra careful about this at solar installations. Here we see a supply side disconnecting means that has a proper neutral to ground bond right here. You can see. And you can clearly see the white neutral conductor entering from the top on the left side, and the green bonding screw effectively bond the neutral to the enclosure, and that's done properly. You should always make sure that the terminal lugs within electrical panels or electrical equipment they only have the max number of conductors that they're rated for. Here you can see breakers and lugs that have multiple conductors installed in them, even though they're not rated for that. And you also want to keep in mind what size conductors the lugs are rated for. If they're too large or too small, then they can potentially not have a good connection, and if the wires are loose, then that provides potential danger. All right, so this is a load side connection. This label is required when the 120% rule is used to add additional PV to the bus in excess of its rating. We talked about this for several slides earlier. And so this requires that if you're going to add additional power to the bus, that the source of the PV power be at the opposite end of the bus, so that it doesn't overload the bus, as we've seen already. This would have to be at the opposite end of the panel from the main breaker. And it shouldn't, there's all these labeling requirements for this specific situation. Here we have what's called a feeder tap, and they're a type of interconnection that require special consideration. It's sort of like a hybrid load side connection. And so they have the potential to add additional available current to conductors and bus bars. And you have to consider this when you're looking at this design. In this case, in order to protect the conductors from the additional PV current, an additional overcurrent protection device has to be installed. So this is the added breaker that they put in. And this is covered in Article 705 of the code. Here's a real life example of the previous slide. We see the interconnection on the load side of the 200 amp breaker. So this is where the load is coming in. And this is at an apartment building where the apartment panel didn't have a main breaker. This is in the meter pan, and it has the integral disconnect. So the existing conductors can be strained by this additional current. So possible solutions include increasing the size of the conductors in the bus bar for the new additional current, or having additional protection by adding an overcurrent protection device before the load, such as a main breaker in the panel this feeds. That's pretty expensive. but it's a potential solution. You'd have PV voltage tapped into the utility line coming in, and those taps connected to a disconnect. That's potentially possible. That would be if these were connected in above here, I believe, because this is the conductor going into the building, so that's going into the apartment, and the main breaker is right here. So you're adding in additional current, which you would not otherwise have, and this breaker is not protecting against. And so this is not super common, but there are places that you might see it, and you have to be cognizant of that. The left-hand picture is of an improperly sealed roof penetration. The contractor drilled through the roof, and then rather than sealing it properly with this piece of equipment, which we saw earlier, they used this like construction putty kind of, which is duct seal, to seal the opening. That's not really a good way to do it. It'll eventually, wear away, and it's somewhat weatherproof, but not great. So you'd want to use this thing and make sure it's installed properly. We're like 5 slides away from the end, so I'll get through these last few. This I think is kind of the most interesting error in this presentation. These are 2 pictures side by side of the same panel. This is installed outdoors. You can see one side of this looks a lot better than the other side. And this lug over here on the right is discolored. And what happened is the contractor did not tighten the lug. So this was just loose in the lug, and it would sometimes have a good connection, sometimes a bad connection. And so the wire would heat up and cool down, heat up and cool down, heat up and cool down, and it caused failure of the insulation of the wire. And then the wire was exposed and it's outside, so it's very moist and it corroded. And then pieces of the corroded copper started falling off, as you can see here. And, the only way to fix this was to tear it out and replace the whole thing, because who knows how much of that corroded copper got behind the breaker panel. It could be in places where you can't take it out, and it could cause electrical problems, so they had to replace the whole thing. So you have to make sure that the lugs are properly torqued down. That's in the code. Here's just kind of something that we put in for interest. This is a situation where there was a natural gas explosion. I think it was near Boston, and pretty much the whole house is in pretty bad shape. However, the roof is still in pretty good shape, and so some people think that the racking systems used for these things actually provide structural value for the roof and it make it more sturdy. This is not really something that you would likely have to deal with. It's, as I said, it's just kind of put in for interest, but structural issues should be addressed by a PE or registered architect. Now we have just a couple new products, and then we'll be done. This is what's called Connect DER. It's something that was used in the Con Ed territory, and it's the point of interconnection for the PV system, and it also gives the utility real-time solar generation data for forecasting, which is handy for the utility. And it also the connection is made outside your house, so the installers don't even have to enter your house. Everything can be done on the outside of your house. No one has to come in. And so that's maybe where things are going for PV installations. That's just interesting. Here's micro flashings, which I don't know how common they are, but I've heard they're super useful. They're used to sort of mount the racking systems onto your roof. Normally you would not want an electrician coming through and doing work on your roof, but if this helps them to do it more quickly and it's just as good, that's great. So they may become more popular. Here we have a bunch of resources, provided by NYSERDA. As I mentioned earlier, the Solar Guidebook. You have all the reference guides and checklists and things from NYSERDA Quality Assurance. And you have the Energy Storage Guidebook, as I mentioned, that may become more and more common within your jurisdictions throughout the, next few years. These are all great resources. Again, the links will be in the presentations sent out to everyone, hopefully. If you have any questions, you can also email me. And but definitely use these if you can, because they're great resources. And so this is the last picture. We don't really have a ton of time for questions. I could take them if people have them, but this is Hudson High School. And they have a solar array on their property. You can see over here, and it's a 1.2 megawatt system, and you can see it's kind of a smidge bigger than the athletic field right here with the track around it. So it's just kind of a good visual for how big these systems are. So a 1 megawatt system is about as big as a football field with a track around it. It's like 3.5 acres. So with that, I can take any questions if there are any. I didn't see in the Q&A if there's anything. It doesn't look like it. But that's all I have. So thank you for listening, and thank you for having me to present.
Chris, thank you.
Yes,
Nope.
thank you, Chris.
I just had one question I wanted to ask you. This might
Sure.
be a little bit off your content a little bit, but I've been talking to Haley about this recently. Is one concern I have is, well, a couple of concerns. One is, we're going to have trillions of solar panels that are all going to go obsolete at the same time. So the disposal factor and how that's going to work, I don't think anybody has an answer to that. I know there's couple of startup companies out west that are trying to come up with a system of taking an obsolete panel and disposing of it in a responsible way, but there's nothing on a mass scale that I'm aware of at this point. And then the other part of that is the decommissioning of the sites, and we have a lot of whenever you have an industry that's heavily subsidized with public funds, you're going to have all kinds of new companies popping up out of nowhere. And these one-off LLCs that are set up to basically own and operate these solar farms in many cases. And I understand, there's decommissioning bonds, there's different things that are in place. But what happens when a private landowner has one of these on their property? Could be of any size, 1 megawatt, 7, 20, whatever megawatts. And that company that they have the agreement with goes out of business after a certain number of years, 25 years from start to finish, the panels are obsolete. What kind of guarantees are there in place? Does the state or NYSERDA have any programs where they're socking money away somewhere to act as a backstop when companies go out of business before these solar farms are obsolete, to make sure they get cleaned up?
Those are great questions. I don't know of any sort of NYSERDA fund or anything like that for backstopping the solar companies, or like you said, they have a lot of LLCs that they bring into existence for specific projects. That's a great question. I should I'll try to get an answer for you from NYSERDA. And then for the decommissioning of the systems, I know that there is a lot of effort sort of being put forward to figure out how to recycle the panels, because they're very expensive to make, and they some of the metals in them are sort of precious metals, so they want to recover that as much as they can. And so the good thing is, they're warranted for like 25 years, but that's typically after 25 years they'll only produce like 80% of their rated capacity, so they're still going to be able to produce and still most of the capacity. So likely they will stay in place, or at least you won't have a situation where, like, we installed 10 million panels this year, we have to get them all out in 10 years. It'll be gradual. I think it'll be more gradual.
Well, but those are new panels that are installed based on today's financial calculations. Now, as I understand it, after 10 years, they start to degrade, and they're producing less energy. So even if you get to 70 to 80% at some point in a couple of decades, factor in inflation and everything else, are they going to be able to provide a return on investment that's worthwhile enough to the operator, especially in an area like New York? We're not Arizona, we're not California or Florida. So so if you take what they're producing throughout the year on average, and you cut that by 25-30%, is that really going to be financially viable? I mean, I guess that's something we don't know at this point, but but as they continue to degrade, at some point they're going to need to be disposed of. And at this point, we're not even allowing mattresses in landfills. I don't know if people are aware of that, but if mattresses have to be recycled, and there's only a couple of places to do it. I think the nearest one for us is Connecticut. So they have to be separated out from the trash, and they have to be recycled. So as we continue down this route, because the Northeast is very quickly running out of landfill space, so obviously we need to move to something different, and the panels are going to really present an incredible challenge in the future.
I agree. Yeah. And I mean, I'm fairly confident they'll find a way to repurpose them, or to recycle them. I know, like I said, I know there is a lot of effort going into that. But at the same time, I agree with you. I don't think they've come up with a solution, but
I'm not trying to pile on you here. I just figured I'd ask, since you were this poor guy. He came to talk about technical stuff, and I'm hitting him with all this.
Trying to set up solar policy for the next 25 years.
Yeah. Well, I do think it's things that we need to talk about and think about. We're certainly in a rush to throw these panels in. Are we really ready for what's coming next? I don't know.
Yeah, it's definitely something that we need to think about.
Great.
Well, I don't see any other questions in the chat, so I think we can wrap it up now. Thank you, Chris, for presenting. Thank you, Chairman Barrett, for hosting, and thank you all to the attendees. And there will be a recording and slides available to everyone. Have a nice rest of your day.
Thank you, everyone.
Thank you.